The
first speaker is Dr. Robert Heath Dennard, laureate in advanced technology. Dr. Dennard, please come on the stage. Prior to Dr. Dennard's lecture, we will now introduce his profile. Please watch the screen in the front of the stage. Dr. Robert Heath Dennard was born in Texas, United States in 1932. He was the youngest of 4 sisters and brothers. He spent an active childhood riding horses and climbing trees. This is a picture of him with his parents. His father was a dairy farmer who cared a lot for his family. His mother used to cook a special dinner on Sundays, which was a big treat for the family. This is Dr. Dennard in his high school days wearing the uniform of the music band. He used to play the bass horn. He displayed his talents in mathematics and science, and at the suggestion of his guidance counselor, he chose to study electrical engineering. After receiving his PhD in electrical engineering from the Carnegie Institute of Technology, now Carnegie Mellon University College of Engineering, in 1958, he then joined IBM. He started to engage in research on the semiconductor memory from this time period, which is often referred to as the dawn of computing. In 1967, Dr. Dennard invented the basic structure of the semiconductor memory, which is known as the DRAM. The basic structure is a very simple one, making up the memory cell with 1 transistor and 1 capacitor. This invention led to a remarkable increase in the memory capacity and throughput of digital information. In 1974, 7 years after his publication of the DRAM, Dr. Dennard and his colleagues at the Research Center published the scaling theory, the design guidelines for transistor miniaturization. The theory says that the operation of the transistor is guaranteed when the length, width, and height of the transistor are reduced by the same proportions, and when the voltage is also altered by the same proportion. This has contributed greatly towards higher integration, higher speed, and lower power consumption of the memory IC. The DRAM, which is the main storage device for digital information, is widely used in all sorts of equipment surrounding our lives, including the PC, cell phones, and digital camera. The current major interest of Dr. Dennard is on clean energy supply and environmental issues. He is providing advice on research for ultimate enhancement of energy efficiency of semiconductors. He gives the following advice to young people. Education is indispensable to being able to make significant contribution in the science and engineering field. Realize that what you do can make a difference and take advantage of that. Dr. Dennard and his wife Jane. They have 2 daughters and 4 grandchildren. They are very happy to have the opportunity to visit Kyoto's beautiful parks, shrines, and temples again. Dr. Dennard will look back on his career as a researcher and will tell us what is most important to bring about big inventions and the implications of what is required as the basic characteristic as a researcher. The topic is reflections on creativity in my microelectronics career. Dr. Dennard, please.
I'm very happy to have this opportunity to speak to you. I will talk first about my formative years, my childhood and my education, and then about my most creative years in microelectronics and how microelectronics evolved over the years to have such an astonishing impact on society. I will close with an update on an essay on creativity I was invited to write in the year 2000. Looking at opportunities and challenges for the new century and beyond into the new millennium. I was born in a small town in Texas in 1932, in the middle of the Great Depression, to a loving family of very modest means, but great pride. By the time I was growing up, we had moved to a small farm in a rural area in East Texas and lived in a house which did not yet have electricity. My father farmed the fields and raised the livestock, while my mother kept us fed and provided with clean clothes. I started my education in a one-room schoolhouse with 3 grades in different rows of desks. After a couple of years, I moved to a little larger school where my 4th grade class was in the same room with the 5th grade class. Learning came easily to me, so I had a chance to hear what the higher grades were doing and advance at my own pace. My older sisters and brother had grown up and left home, but they visited frequently and provided great role models. I remember long summers with a lot of free time to think and entertain myself. In the early 1940s, when World War II came, my father saw an opportunity to move our family to a small town just outside Dallas. I now attended bigger schools and lived in a community where I could visit and interact with classmates. I also found the library and became an avid reader. When my sister Evangeline went away to become an Army nurse, she left behind her collection of books and phonograph records. I was totally impressed with a large red book, which was an anthology of science fiction stories. I read them all with pleasure, and I particularly enjoyed those by H.G. Wells, which stimulated my young imagination and formed vivid images of strange worlds and people. I was very amused by a book of Ogden Nash poems, which I read and memorized. There was also an album of Sigmund Romberg operettas, which fascinated me. I sang along with them, and I also memorized the words and tunes. This most likely was the starting point for my love of choral singing and all forms of music. While I loved sports and played baseball and touch football with my friends, I was not big enough or fast enough to compete in high school team sports, which were heavily emphasized. Luckily, in my sophomore year, a high school band was started, and I became a member. I played French horn at first, and later I switched to a bass horn, which was needed in the marching band. As I was finishing high school, I chose my future career as an electrical engineer with the help of a guidance counselor. She advised me that electrical engineering was a fast-growing field, and she said it would be good for me because of my mathematics aptitude and my interest in science. I planned to go to a nearby state junior college along with many friends. One day, an important thing happened which changed my life. The band director at Southern Methodist University in Dallas came to visit me and offered me a band scholarship to come to the much better school. His advice was, why not take the best opportunity available to you? That was a striking idea to me that helped guide the rest of my life. It helped me to go on from SMU to Carnegie Institute of Technology in Pittsburgh, a top engineering school, which is now Carnegie Mellon University. And from there, when I got an opportunity to join IBM, at the time its Thomas J. Watson Research Center was just being started, I didn't hesitate. After a learning period in research, I feel very lucky that I got involved in microelectronics in the middle of the 1960s. I would like to tell you something about the invention for which I am being honored, how it came about, and where it fits in the broad context of microelectronics. First slide, please. This chart by Professor Sa, a pioneer of the field, defines 3 different phases of microelectronics. Phase 1 includes the invention of the transistor and its early use as a discrete device replacing a vacuum tube. Phase 2 began with the concept of the integrated circuit, using microimaging techniques to fabricate many transistors, other components, and wiring connecting them together on a tiny silicon chip. 10 years were taken to develop this technology and actually make it work. The third phase, beginning in 1969, saw the deployment and continuous improvements in microelectronics, which has continued ever since. I got involved in the second phase of microelectronics in the middle of the 1960s. I was assigned to work in a group at IBM Research, which was developing a new kind of transistor called a field effect transistor. These transistors were also called MOS transistors, for metal oxide semiconductor. That name describes their structure, a metal gate over a thin oxide insulator on a semiconductor substrate. My particular small group had the task of learning how to use this newly emerging type of transistor in integrated circuits built on silicon substrates to perform computer functions. The big goal was to replace the magnetic core technology used in those days for random access memory called RAM. In those memories, small loops of magnetic material, very much like beads, were strung together using wires into large two-dimensional arrays. Each of these beads could be magnetized to store 1 bit of data. The largest memory in the largest IBM mainframes at that time was 1 megabyte. The clock rates were hundreds of kilohertz, and the power consumption was 40 kilowatts. We had a proposed way to build memory with our MOS technology, which used 6 transistors, 6 MOS transistors, I should say, and a flip-flop memory cell to store each bit. We hoped to integrate 128 of these memory cells in a small silicon chip. One day in late 1966, an important event in my life occurred. During the day, I attended a large IBM research conference where various projects were presented. I was very impressed by a description of a proposed thin film magnetic memory, which was projecting hundreds of thousands of bits in a 25 centimeter wide memory board. What impressed me is fundamentally better about their approach was that they had a very simple memory cell, just a small square of magnetic material at the intersection of 2 etched copper lines. I was inspired to find something that simple for the technology we were developing. I went home that evening pondering analogies between magnetic circuits and electronic circuits. I considered the possibilities for using a simple capacitor as a basic memory element, storing a binary bit by charging or discharging the capacitor to two different voltage levels. Next slide. This slide shows the simple circuit I discovered. A capacitor, as suggested by its symbols and the drawing at the top, is just two conducting plates separated by a thin insulator. I found that an MOS transistor in series with each capacitor could be used as a switch to connect the capacitor to a data line briefly to charge or discharge it to write a data bit represented by a positive voltage level plus V or a 0 voltage level on the bit line. The transistor is turned on and off by a control signal on a word line that allows selecting a given capacitor from many others for receiving the data on that bit line. In my initial thinking, the capacitor was the gate of another transistor, and reading was accomplished by monitoring the current flow in that second transistor. I was very excited about this idea, but it wasn't as good as I wanted. It required multiple access lines with complicated drive schemes, or an additional transistor to make a memory array function properly. I kept working on various configurations for a few weeks until I finally realized that the stored charge could be read back out through the same transistor through which it was written, which would create a small detectable signal on the bit line. The cell had been reduced to a single transistor and a capacitor at the intersection of two access lines. I was satisfied that this was as close to my goal as possible and offered a great reduction in complexity compared to the 6-transistor memory cell. The drawing below shows a cross-section of a field effect transistor and a capacitor forming a 1-transistor memory cell. I won't attempt to describe this in detail. A beauty of the integrated circuit is that the conducting layer forming the gate of the transistor is common to all the gates, so that it also serves as a wire selecting a particular row of cells. Also, one doping region in the silicon is both the drain electrode of the transistor and serves also as one of the capacitor electrodes. A distinctive characteristic of this memory cell is that a small leakage current from this N-doped region to the P-type silicon substrate discharges the capacitor in a fraction of a second. This gives rise to the name dynamic, since the data is only stored temporarily. To preserve the data, it must be refreshed by reading it out and writing it back into each cell at certain intervals. Fortunately, the speed of this memory scheme allows more than 100 million read or write operations per second, and only a small percentage of these are needed for refreshing the data. Thus, this scheme became known as dynamic RAM, and commonly called DRAM. Next slide. This slide shows a drawing from the US patent, which I was granted for this work in 1968. It shows a small array of memory cells connected to circuits for supplying the data and for selecting a particular row of cells. My management at IBM understood the potential of this new invention, but it was considered too risky for the technology at that time, which was still leaky and unstable. So I went back to work with a few others to design and prove a prototype of a 512-bit chip using the 6-transistor cell. Later on, this 6-transistor cell came to be called static RAM, after a dynamic RAM was named. In time, we completed the research and development work on the MOS transistor process, wrote up a design manual, and transferred it to manufacturing. Eventually, in the early 1970s, IBM shipped the first computers with semiconductor memory using the more established bipolar transistor process, and the MOS static RAM won out in the next generation because of its greater density. In the same time period, various versions of dynamic RAM began to appear in the industry, at first with several transistors per bit, like a popular product from Intel. I finally got a chance to work on my one transistor dynamic RAM scheme in 1970, when a new project was started at IBM Research with the ambitious goal of drastically reducing memory costs by combining the simplicity of one transistor memory cells with a substantial reduction in all the transistor and wiring dimensions of the integrated circuits. My longtime associate, Dale Critchlow, was the leader of this program. We wanted to take advantage of dramatic advances in lithography techniques which were being developed at our laboratory, such as electron beam pattern writing, which we felt could reduce the dimensions used in integrated circuits by a factor of 5. One of the practical problems we had to face was how to design MOS transistors with such very small dimensions. We knew that just reducing the size caused them to switch on and off poorly. My small group responsible for the MOS transistor design considered all the problems, and it soon became clear that there was a general way to design smaller devices which involve scaling down of a few key parameters. This is illustrated in the next slide. We found that reducing the applied voltage, V, and increasing the silicon substrate doping concentration, N, by a certain scaling factor, alpha, allows all the dimensions of the MOS devices to be reduced proportionally. The smaller transistor on the right has the same electric field patterns as the transistor on the left, so it behaves in a similar way and turns on and off properly. Also, we plan to scale down all the interconnect lines by the same amount to get much denser integrated circuit layouts. It was a remarkably simple and concise process, yet very powerful. It told us our miniaturized circuits would switch faster and also use much less power. We built a lot of very small devices, scaled by a factor of 5, to confirm the theory and to understand the limits. I presented this work at the International Electron Device Conference in 1972. Just a few months later, at the International Solid State Circuits Conference in 1973, several companies, including IBM, were showing the first early versions of memory chips using my one transistor dynamic memory cell. The acronym DRAM, pronounced DRAM, came to be used for this type of memory. At the same conference, my associate, Dr. Wan Yu, demonstrated a small array of DRAM memory cells scaled 25 times smaller in area by using electron beam pattern writing. Dr. Yu, along with me and other authors, followed up by publishing an entire experimental 8 kilobit DRAM chip with these deeply scaled dimensions in 1975. Next slide. This slide shows a greatly magnified photograph of some memory cells in that chip. The light-colored vertical shapes are the aluminum word lines. They're connected to small square features, which are the transistor gates. The horizontal shapes are the bit lines and the top electrodes of the capacitors. Next slide. This slide shows the cover of an issue of Nikkei Electronics in 1976, which contains a reprint of our 8 kilobit DRAM paper as described in the upper right corner of this cover. Next slide. This slide shows the first page of that reprinted paper about the deeply scaled 8K-bit DRAM chip. This paper and our related work on scaling has been cited as key to key factors in the establishment of a large national program in Japan called the VLSI Program for very large-scale integration. The impact of that program has been huge. I first visited Kyoto to attend a symposium on VLSI technology, an international conference which is still held in Kyoto or Honolulu on alternating years. Circuit design and innovations also played an important role in the development of the dynamic RAM. The main difference between the dynamic RAM and the earlier static RAM was the need to sense very small signals coming from the memory cells onto the bit lines when a given word line was activated, and to write the original voltage levels back into the memory cells after this destructive read. For some time after my invention, I had the notion that I could use off-chip bipolar sense amplifiers like we had used with our previous static RAM chips. Even for the small arrays which were appropriate to the design and ground rules of those days, the number of terminals which could be assigned to bit lines represented a big limitation to that. We knew that on-chip sensing circuits were desirable, but there was very little experience with MOS circuits for sensing small voltages. The variation in the threshold voltage, the gate voltage required for turn-on, was quite large in those days. One day, Dale Critchlow came around to discuss some balanced latch circuits he had heard about, which I believe were being used in touch-actuated keyboards to sense small changes in capacitance, which would unbalance the latches. Other people were also working on similar latches at that time. Next slide. This slide shows a paper by Stein and others published in 1972. The sense refresh circuit in the center contains a latch circuit connected to two bit lines on opposite sides of the latch. Both bit lines are connected to a large number of DRAM memory cells. Before each memory access, transistors in the sensing circuit balance the voltage on the two latch nodes and the bit lines connected to them to an intermediate voltage level. Then, raising the voltage on any word line in this array turns on the transistor in the associated memory cell, causing the capacitor connected to it to charge or discharge a bit line, so the latch is unbalanced in a direction corresponding to the voltage stored in the memory cell. The beautiful thing about the latch, when it is activated, is that the small signal unbalance is amplified up to full digital levels. And those levels are fed right back onto the bit lines where they're written into the memory cells to restore the original levels. This seems to me to be one of the most fortuitously efficient circuits ever devised. As far as I know, the balanced latch has been used in one form or another in all one-transistor dynamic RAM chips after the first 4 kilobit chips. There have been many improvements and variations. Next slide, please. The de facto standard for many generations of DRAMs is this folded bitline arrangement invented by my esteemed colleague, Dr. Kiyu Ito at Hitachi in 1974. He took the two bit lines shown on opposite sides of the latch in the previous drawing and folded one over to the opposite side along with its word lines and DRAM cells to form pairs of bit lines being crossed by pairs of word lines, as seen in this slide. The advantage he discovered is that noises introduced on the pair of bit lines are effectively canceled out by this arrangement. Starting in the middle 1970s, our group in IBM Research, led by Dr. Critchlow, worked closely with a manufacturing team in Burlington, Vermont, to develop IBM's first one-transistor DRAM chip product, shown in the next slide. slide 10. The technology developed for this chip was scaled sufficiently to be able to produce a 64 kilobit chip. The sense amplifiers shown on this slide were based on a new self-compensating design technique invented by my associate Dominic Spampanato and myself. I also contributed to a new technique for adding redundant bit lines and word lines, which can be used to replace defective lines to greatly improve manufacturing yield. This technique has been widely used for both DRAM and static RAM for many generations since then. I was asked to identify difficult challenges in the progression of my work. Just at the time of the production of 64 kilobit chips was being announced, and the dynamic RAM seemed to be getting very mature, the world was becoming aware of two very significant papers. May and Woods of Intel and Yaney, Nelson, and Van Skyke of Bell Laboratories reveal that some 16 kilobit dynamic RAMs were suffering transient errors due to bombardment by alpha particles. The alpha particles were identified as coming from radioactive impurities in the materials of the hermetically sealed packages. At first, it seemed to have a simple solution. Why not modify the package or introduce a barrier layer, such as a plastic film, between the chip and the package? When experiments like these were done in various labs, the error rates dropped substantially, but did not go away completely presumably due to radioactive impurities in the on-chip materials. Also, an analysis of the possible soft error rates due to cosmic rays showed that this source could be significant. Here was a real crisis. Not only were hordes of people scurrying around to fix up designs of chips then in development or manufacturing, but the whole future of miniaturized MOS integrated circuits seemed to be in jeopardy. Personally, I felt very responsible because of my early role with dynamic RAMs and because I failed to anticipate the problem. Several years earlier, I had discussed the possible effect of cosmic rays on dynamic RAMs with an old friend who was knowledgeable about space electronics, but we had concluded that most of the radiation types would pass through with little effect. After a long period of doing measurements, developing models, and inventing possible cures, a less threatening view of alpha particles and cosmic rays evolved. A good quantitative understanding was provided by various modeling techniques which were developed, including a very powerful Monte Carlo approach developed in my team by my associate, Dr. George Sahilas. It was shown that error rates would rise in response to scaling to smaller dimensions, but that design changes, including error correction techniques, would contain the problem. The midlife crisis was over. As the idea of scaling MOS transistors, along with all the layout dimensions, interconnect lines, etc., caught on quickly, the microelectronics industry developed a pace for doing this, which has given rise to the geometric growth in computer capability since then. Moreover, DRAM became the large volume, productible chip which drove scaling in silicon chip manufacturing for many years. Next slide. By now, I'm sure that you understand DRAM has experienced tremendous productivity increases, which has allowed quadrupling of the number of bits per chip every 3 years for many generations. This figure shows pictures of 6 generations of IBM chips and shows the reduction in cell size, which allowed the increased number of bits. Much of this reduction is due to decreasing all the dimensions of the transistor and wires using the scaling principles. The DRAM cell has been compacted further by making technology improvements which reduce the memory cell area. Next slide. Next slide. This slide shows a big breakthrough started by Dr. Hideo Tsunami when he published a paper showing DRAM with a three-dimensional capacitor formed in a trench etched in the silicon substrate. Starting with the 4 megabit chips, all the DRAM produced by IBM has used a trench capacitor technology. Next slide. Another three-dimensional capacitor structure called a stacked capacitor is fabricated above the surface rather than below. This technique was pioneered by Dr. Mitsumasa Koyanagi and has been used widely in the DRAM industry. Next slide. This is a good place to introduce a special picture made at the 2006 annual award ceremony of IEEE, the Worldwide Professional Society for Electronics Engineers. The picture shows from the left to right Dr. Ito, Dr. Tsunami, me, and Dr. Koyanagi. They were being honored with the Junichi Nishizawa Medal, and I came to celebrate along with them. Notice the fanciful caption at the top of this picture, "The DRAM father and his 3 sons in scaling law." I believe it was supplied by Dr. Tsunami. That was a wonderful night. Not long after that, we all wrote articles for a special issue of the IEEE Solid State Circuits News, which was totally dedicated to DRAM. You may have noticed that part of the DRAM productivity increase has been due to using larger silicon chips. This has required larger silicon substrates called wafers for best manufacturing efficiency, as illustrated in the next slide. Next slide, please. Over the last 30 years, the silicon wafer diameter increased from 25 millimeters to 200 millimeters, as shown here. I should have said over the first 30-year period. Next slide. Since then, most of the big new factories have used 300 millimeter wafers, as shown in this photograph. I hope you realize how it feels for me to hold one of these wafers. It's actually very light. Today's 300 millimeter wafers contain hundreds of 4 gigabit DRAM chips. As you can see in this picture, I'm very proud of what I helped get started. The growth in size of chips and the increasing number of transistors and circuit elements on a chip followed the path known as Moore's Law, which is named after Gordon Moore, one of the Intel founders who predicted it in the early days. As the complexity of those chips increased, it became very difficult to implement all the numerous wiring connections among the transistors, the logic circuit inputs and the logic circuit outputs. It became necessary to provide multiple layers of wires. These were organized with all the wires on one layer running perpendicular to the wires on the next level, like streets and avenues in Manhattan in New York. As scaling progressed from one generation of chips to the next, the widths of all the wires were scaled down, along with the transistor dimensions, as the scaling principles we discussed earlier suggested. But this made the wires much more resistive for a given length of wire. Some of the wires which had to connect longer distances across the bigger chips got very resistive, and the signals propagated very slowly on those wires. Many people thought scaling was nearing an end because of this problem. To me, it was another crisis which needed attention. Next slide. I remember giving some lectures at Stanford University in the 1970s where I proposed the hierarchical wiring structure illustrated here. The highly scaled small wiring layers next to the transistors in the silicon substrate are only used for very local connections of elementary logic circuits. Wiring layers in the middle with thicker and wider metal winds have much lower resistance, so they can be used for long connections between different blocks of circuits. very large and thick wires in the top layers can carry high-speed signals all the way across the big chips to connect various processor functions and memory subsystems together. Other thick wiring layers at the top can be used to bring in power for the chip and to distribute clock signals across the whole chip to synchronize the processor functions. A lot of analysis and modeling was done at Stanford University and elsewhere to show that such a system can work. It has been used in many generations of MOS technology, gradually adding more layers with even smaller scale wires at the bottom and even larger and thicker wires at the top. Also, a whole new set of materials were introduced with copper wires for lower resistance and better insulator material for lower capacitance. Next slide. This picture shows a highly magnified cross-section along the wiring layers in a chip with the new copper wires first introduced by IBM. You can clearly see the smaller wires in the lower wiring planes and the larger wires in the top planes. Next slide. Here is a scanning electron microscope picture of some of the lower level wires with the insulator layers etched away to show how wires in one direction are connected to wires in the perpendicular direction. Today's latest, largest processor chips have as many as 14 wiring layers, and the billions of interconnections use a total of about 40 kilometers of copper wire. These wires are truly as important as the transistors in making integrated circuits work. Since I became an IBM Fellow in 1979, my career after that has been spent on helping Deram and Scaling continue to advance, generalizing the scaling rules to certain respects, and finding ways to live with some of the scaling limitations we were already able to predict in 1972. These limitations include the increased need for materials with better conductivity and the inability to scale the voltage much below 1 volt and still have the transistors switch on and off cleanly. These problems have caused a leveling off in processor speeds over the last 10 years. Work has continued to bring in improved structures to allow further scaling down of the transistor and wire dimensions. The main goal now is to improve energy efficiency to allow large data centers with thousands to millions of processors to provide more computing for a given amount of energy. I plan to discuss this issue and what I see as the best technical path towards solving it in my talk at tomorrow's workshops. I'm very proud to say that with many process improvements, structural innovations, and plain hard work, the thousands of people who make up this industry have been able to achieve in 40 years a reduction in all dimensions of integrated circuits by a factor of about 150, and still more is expected. The results of that, the ways that computers have advanced and changed our lives, has been truly amazing. Can you imagine that I used a slide rule to design my first memory chip? The point of bringing that up is to ask the question, what will the world be like in another 40 years? This is the challenge and the opportunity for the young people in the audience here today who are just starting their careers. You also have a chance to create a greatly different world in your time. The tremendous progress in science and technology in the last millennium and its rapid acceleration in the last century is due to the remarkable creativity of mankind. Yet so little is known about creativity. What is it? Who has it? How can it be stimulated? Apparently so little is known and understood about this subject that it is assumed that a person like me with some demonstrated record of accomplishment in creativity can say something interesting and useful about it. So I've decided to suspend my normal humility and accept the challenge to talk about my own personal thoughts and experiences in this area. Above all, creative people cannot resist a challenge. So what is creativity? It is an intellectual capacity of some human beings, something that goes on in the brain, something not yet matched by computers. According to my understanding, it is the ability to produce or bring into existence something that was not there before, something new, an extension of our base knowledge. In other words, for those of us who have undertaken research as a career, it's a necessary trait to excel in our jobs. Most of my experience has been with the extension of scientific or engineering knowledge and capability, but I suppose some of my observations may apply to artistic fields as well. My experience with creativity is it can produce a sudden leap into the new and previously unknown. I often wake up in the middle of a night with a solution to a problem which I have been working on previously. Many inventors have described similar experiences to me, including getting out of bed to make notes or drawings before going back to sleep. Others have described significant inventions made while driving, which apparently leaves a lot of the mind free, at least before cell phones. As I described previously, my invention of the DRAM memory cell came early one evening after I came home stimulated and challenged from listening to a talk about a competing research project. The basic idea came in a moment, and there were a couple of months of perfecting it before the final simplification to a single transistor came in another flash of inspiration. Who has creativity? I know from experience in following careers of associates in similar environments over long time periods that some are creative and others are not. The ones who are not creative can be equal or superior in analytical capability, well organized, good communicators, and overall very solid and useful individuals. But research institutions are measured on their creative output, so it would be good to be able to identify creativity in employment candidates. I believe that creative thinking is basically a process of posing significant questions and finding good answers. So I give a lot of credit in interviews to those who ask relevant, penetrating questions. And I also try to examine their ability to apply fundamentals to answer those questions. I know that there have been some attempts to develop profiles of creative people using questionnaires, but I don't know how successful these have been. I've been fortunate in recent years to be included in groups of people who were receiving major honors for significant creative achievements, and I find them very interesting, but apparently ordinary people. At a National Inventors Hall of Fame event, while I was talking with 4 other inductees, I discovered that all 5 of us were raised in rural areas or small towns, and most started their education in one-room schoolhouses like myself. We all were left on our own with plenty of free time to develop our ideas about life. And now that may not be the key to our subsequent successes, but surely it is a counter-argument to many of the things which are considered necessary for the younger generation today. I developed a very slow thinking process in my early days, and I believe that I was able to bring a great concentration to a problem and engage my whole brain in finding a creative solution. I have a motto pasted in my bedroom where I see it every morning, which reads, "Attitude is everything." It was given to me by my ballroom dance teacher, but it applies to many other pursuits. I believe it is the key to unleashing creativity. A great many have the intelligence, many have the preparation, some are at the right place at the right time, and only a few realize that they have the mission and ability to make a major difference in our world. I believe my attitude was developed with the aid of some influential people at every step who urged me to pursue the best opportunity which was available. At the PhD level, my thesis advisor made me aware that I was expected to become the world's expert in the subject of my research. When I joined IBM in the late 1950s, there was a clear mission to advance the computer art. We were issued engineering notebooks to record our patentable ideas and told to invent. Our early projects, in hindsight, were a little far-fetched, but we pursued them with enthusiasm. In the mid-1960s, as I told you before, some of us were assigned to do the engineering for a modest-sized program trying to exploit the very new MOS technology. It was a tough technology, but it had great potential if we could solve the problems. My manager told me to find the best way to do memory with this technology. I was ready. I had a very good attitude. I had been groomed and motivated at every step. I was working on the right project at the right time, and I knew my mission. Today, times have changed, and the technical opportunities are in different areas. I believe that motivation and leadership remain essential to nurture creativity and provide an environment where it can flourish. Is there a need still for creativity? Yes, of course, in a general sense, the need for creativity in the future is obvious. On the other hand, if we look in some detail at where the world appears to be headed, we can readily see that the need is indeed critical. The rapid pace of industrialization of the previously undeveloped nations and the projected growth of populations is leading us to a time where there will be severe impact on the resources and environment of our finite globe. Surely future generations must be preoccupied with understanding and mitigating those effects. Major advances are clearly needed in energy supply and distribution. We must face a crisis of limited supply of energy resources and major environmental deterioration due to using it. The field of transportation, which has seen such major advances in the past, is clearly not on a course which is scalable to the future needs of society due to its high energy demands. Also, the really big problems of the past remain. Future generations must still face disease, hostile fellow humans, and natural disasters of a tumultuous Earth and a chaotic universe. These challenges present a broad range of opportunity for creative solutions where meaningful goals can range from complete cures to merely improving chances of survival. Are there needs for further creativity in information technology, the means for generating, distributing, and presenting information after the major advances in communication and computing capability in the last half century? Yes, because these tools have become indispensable to economic productivity and can play a major role in the solutions to the important problems which I described. Where will creativity lead in the future? Every trend curve says that the pace in science and technology, like the stock market, will move ever onward. But we, like every preceding generation, have done everything we know how to do and are unable to see much beyond the next steps which are already in place. We must also consider the possibility that our last century's prodigious progress has seriously depleted the pool of unknown knowledge left for future scientists to bring forth. Certainly, it appears that there are a limited number of laws of physics and chemistry governing our universe and a limited number of basic elements. We may be close to completing our understanding of the essential implications and properties of all of these. Therefore, the future may not hold surprises so fundamental as the radio and the transistor. However, the advances of the future in the physical sciences will likely still be astounding in their impact on society. Hopefully, this will include some breakthroughs that allow nuclear power to be fully harnessed. Also, computers will likely be devised with so much creative capability, the question of whether they think will become irrelevant. The biological sciences appear to be breaking forth into their golden age. The questions there are not how far they can go, but how far should they go? In summary, whether or not we understand exactly how human creativity comes about, its impact on the world we live in is profound. I'm optimistic that our creativity will give us the knowledge and tools to clean up the major messes and avoid the potential disasters that our technology advances have spawned. Clearly, more than science and technology will be needed in this respect. Hopefully, the global infrastructure which science and technology have provided will help solve the critical global problems facing future generations. In closing, I want to thank the Inamura Foundation once again for this great honor.
Thank you very much indeed. Now to the Dr. Dennard, now flower bouquet is presented. That was Dr. Dennard. Thank you very much again. A big applause.